We'll go on to our next paper. It is being presented by Mr. Anil Kumar of Lloyd's Register, Consideration of Hybrid Technology and Associated Machinery. Mr. Anil Kumar is Principal Surveyor and Area Business Development Manager, South Asia, Lloyd's Register. He is currently in charge of South Asia Business Development for Lloyd's Register Marine and Offshore, focusing on technology, innovation and co-creation with clients, and providing core classification and consultancy services to shipyards, ship owners and navies in India, Sri Lanka, Bangladesh, Malaysia, Indonesia, Thailand, Vietnam, Philippines, and is based in Chennai. Prior to his current role, he was Principal Surveyor and Marine Operation Manager in charge of Lloyd's Register ship business and operation in East Coast India, Sri Lanka and Bangladesh. He was tasked with the role of Lloyd's Register Operation Manager for Sri Lanka and Maldives for 5 years, based at Colombo. He has been in the marine industry for over 29 years in various capacities, rising from professional naval architecture to classification society surveyor and regional in charge. Upon graduation, he worked at Garden Reed Shipbuilders and Engineers, where he was involved in design and construction of ocean-going commercial and naval vessels. While working with Lloyd's Register, he has completed Lloyd's Register Management Development Program at the European Business School, UK. He is also an active member of various professional institutions such as IMEI, IMRS and RINA. Mr. Anil Kumar.
Yeah, thank you very much, sir. First of all, on behalf of Lloyd's Register, and I would like to thank IMEI, the chairman and organizing committee of IMACO, to giving us an opportunity to speak. And my topic, as Professor Cochrane explained, it is consideration of hybrid technology and associated machinery. And there has been, in fact, technological advancement in energy storage and power management systems, and in the form of hybrid technology. The automotive industry has taken lead in hybrid propulsion systems, and the ships, the maritime industry and the aviation is taking early steps towards hybrid propulsion. In fact, this is a paper written by our colleagues based in Trieste as well as Southampton Technical Support Office, and where we look at what are the challenges associated with hybrid propulsion systems and power management systems, and what, as a classification society, Lloyd's Register can provide an assurance to make sure that these systems are safe. So part of my presentation, after a brief introduction, I will look at the drivers for the hybrid propulsion system and the hybrid technology itself, and we will also look at some of the hybrid operating modes for certain designs. And we look at electrical energy storage devices, systems, and class society's approach for providing assurance for hybrid systems, some of the hybrid reference cases, and there have been vessels built with this technology. And we'll also specifically look at a tech scenario and how we can assure that bollard pulls are tested on a hybrid propulsion systems. Basic introduction, the electrical operating vessels, as you know, are not new, and the world's first electrical launches on hire on a series of charging stations was established in 1880 along River Thames. But the battery technologies and battery storage system, hybrid propulsion system has evolved over the time, and it's considered as a alternative for the conventional propulsion system. The diagrams on the left-hand side, on the right-hand side bottom, that is a Scandline vessel operating between Denmark and Germany, and which has got electrical propulsion system and a huge battery power pack installed on that. We are going to discuss that about in a minute. So what is hybrid? And there has been many definitions for hybrid systems, and for automobile industry, it's a conventional engine combined with an electrical motor and driven by a battery. And for the purpose of these sessions, I will look at, for the marine systems, it's a combination of the conventional engines and electrical propulsion system, as well as energy storage devices, and batteries are commonly used there. So what are the drivers? The main drivers have been the environmental related drivers and also market driven. and hybrid propulsion system offers much improved energy efficiency, save fuel, and reduce the fuel consumption, and as a result, reduce the emissions. And if you have a battery-operated supplemented hybrid propulsion systems, that reduce the noise and vibrations. Moreover, there is unpredictable variation in the fossil fuel prices, and in the fossil fuel prices, it's on long-term availability, and there is a requirement to use more of renewable source of energy, so that they are again another drivers. And for ship operators, owners, if they can get rid of one of the generators, for example, on board the ships, supplement by an energy storage system, that will reduce the operation cost as well as the maintenance cost of the machineries. So the MARPOL, in fact, has been putting restrictions on the SOx and NOx emissions, and IMODC is putting restrictions on CO2 emissions. And apart from this, there are countries and port, they are promoting this zero emission port of call concepts. That means the ports are going to be electrified using renewable source of energy. So if you've got a hybrid vessel operating in such scenarios, you can shut down generators when the vessel is in port, and you can use the shore power, and you can also use the shore power for charging the batteries on a hybrid systems. Yeah, there are drivers for this. Just looking at the automobile industry, who has taken a lead in hybrid systems. In fact, automobile industry has got conventional engines, electrical motor driven by battery, and a power management system there, which actually control the power to both the sources, conventional engine and also the battery. This is Toyota Prius hybrid. It's launched in 1997. It's a fourth generation car available as we speak now. So what it uses is the best of both the world. That is best of the conventional propulsion conventional engine, for example, which gives that power and torque, and also the electric motor, and which give the environmental benefits. So this car, when it starts, I'm sure that some of you must be using these cars. When it starts and initial accelerations, slow speeds, you use the electrical motor. That means there is no fuel consumption at all, and there is no emissions. During the harder acceleration, the conventional engine kicks in, but then it charges, it runs a generator, which charges the battery pack, which runs the electrical motor. So the electrical motor supplement the engines for the torque, what it requires. So as a result, you can run a combination of electric motor and engine at a harder acceleration to reduce the fuel consumptions. And when the car brakes, and the energy from the wheels as well as the braking system is, the kinetic energy is converted into electrical energy, which is used for charging, again, the battery pack, which is used as a reserve source of energy. So that's the concept there. There's a difference between this concept and ships when we talk about, and when the ships reduces the speed or want to stop, and there is a lack of adhesion between the propeller and the water, so we can really gain advantage of that kinetic energy converted into an electrical energy to store future use. So hybrid propulsion system, the power production here is from a conventional engine or electrical propulsion. Energy storage could be one of the storage devices, could be a battery or a fuel cell. So when the consumption is lower, the excess energy is stored on board in batteries, and when the consumption, and then it is released when the consumption is higher. So the graph on the right hand side there, the peaks, the plus and minus is managed by the battery. So that means we use the battery power when the consumption is high, and we charge the battery and by running the conventional engine. For example, you don't need to have, for example, a vessel requires 3 generators, and you don't need all the 3 generators. You can have 2 generators meeting the base load, and 1 generator you can remove that generator, put a battery pack, and with the generators and the battery pack, you can achieve the maximum load. Where the base loads can be met just by the generators. And on a very lower speed, when the power demand is very low, you can operate the system with the battery. You don't need the conventional engine at all. So looking at various configurations, the one on top is conventional propulsions. The two sources of power, the main engine drive the propellers, and you've got electrical generators giving power to the ship's systems. And the one on the bottom is the electrical propulsion system, one single source of power, providing power to the ship systems as well as driving the propulsions. And the one on the left top is diesel electric propulsions. It's in DC systems. The one at the bottom is a hybrid with diesel electric systems as well as a main engine, a conventional engine, and both clubbed to the same, connected to the same gearbox driving the propulsion systems. The one on the left-hand side here again, the generator provides conventional AC current to the bus bar, and then you have a shaft generator come electrical motor. You can operate in both the modes using a DC link there, and the AC can be converted into DC to run electrical motor in a hybrid systems, or otherwise when you have the main engine running, conventional engine running, you can use that like a shaft generator and power back the vessel storage systems. The one on the right-hand side is a combination of all. You have a conventional engine driving the propulsion systems. You've got electrical propulsion system driving, the propulsion system again, and you've got also a huge battery pack installed there at the middle, and the vessel can operate on that battery pack. So we look at various hybrid operating mode based on that diagram on the right-hand side. This is the boost mode where you require the maximum power. So you have all the machineries operating in these systems. And this is a diesel electric mode, and where you don't need a maximum power. You can operate the vessel on a lower speed, for example. And parallel mode, and where you got conventional engines as well as one of the generator operating, and the electrical motor is charging the battery back to store the power for the future use. And you've got a transit mode where the propulsion is done by the conventional engine, and same time it's charging the battery. And you got a system where the main engines and generators are shut down, and the propulsion is done by electric energy from the battery itself. And you have a scenario where the batteries are charged from the shore connections when the vessel is alongside. So different operating modes. And looking at energy storage systems, and there are various energy storage systems. For example, we talked about battery. There could be fuel cells, supercapacitor, there are thermal alternatives. But then the battery is been considered as an option as we speak now. But rest of the systems technologies are being developed, and we are supporting manufacturers to see that how we can provide approval for safe usage on board the ship. So looking at batteries, and if you're considering the hazard associated with the battery, we can classify that into an aqueous battery, which are lead acids, or nickel cadmium, or alkaline. Or a non-aqueous battery, which is a lithium-ion battery. And lithium-ion battery is heavily used on a hybrid system because of its high energy density, and also how we can manage the charge cycle much better. And the graph on the right-hand side on the top shows that over the period of time, you can see the lithium-ion battery, the specific energies are much higher than the other source of chemistries. But there are issues with the lithium-ion battery. Thermal runaway is one of them. We're going to touch upon that in a while. So the Ragone plot, the battery engineers use this plot for comparing the performance of various energy storage systems, and basically they combine the specific energy is plotted against the specific power. You can see here the lithium-ion battery has got much more capability than any other systems, which is actually used for hybrid systems, but it comes with its own challenges. We're going to look at that. So the challenges we need to understand, we can break down the hazard associated with the battery in different levels. The cell itself, the battery, and what are the chemistry of the battery, the anodes, the cathodes, the flammability, the toxicity, and the construction of the battery itself. And then batteries are put together as a battery modules. There can be issues which is short circuiting, for example, and control systems and monitoring, and the battery systems, and there can be issues with charging. How do you manage the charging cycle on a battery systems? And at a ship level, there can be issues with air conditioning, ventilation, HVAC systems, the fires, where the batteries are stored. How do we make sure that there are no external or internal fires? So there are various hazards we need to look at when we have a battery systems. Thermal runaway, this is a concept which happened. We are familiar with the mobile phone catching fires, a laptop catching fires. These are all lithium-ion battery. This is being used on board the ship. So what happened is that when the temperature rises to a certain critical temperature, the battery dissipates all its stored energy. It's like a nuclear meltdown, for example. And but then that's how it happens. The diagrams over there on the bottom right-hand side, it started heating, and then it get burned, and there can be external fire on board the ship. Yep. But this can be managed by controlling the battery environment, maintaining the temperature, ventilation, for example, in the battery compartments. So looking at classification society, how do we approach? And we have got rules and regulations, which are prescriptive rules. For example, the ship rules, part 6, electrical and control system, which deals with the AC system predominantly. We also got the provisional rules to address the issues with the DC current, the safety and operational issues. We also written the shipwright procedures, because prescriptive rules are not really applicable to hybrid systems, and there are no real prescriptive rule written at the moment. So we have got a risk-based design assessment process. We also written a battery installation guide for taking care of all the hazards what we have just discussed. So what we propose is an integrated approach, as Mr. Arindar spoke about, how class society is working with the design houses, and looking at the complexities of hybrid propulsion system, battery installation, for example, and how we can mitigate the operational and safety issues associated with that. So as of today, we got a combination of existing ship rules, which are prescriptive, and we use the risk-based design method. And the chart on the right-hand side, you may not be able to read it. They are the hybrid propulsion vessel classed by Lloyd's Register. We assign a notation called hybrid power. There are about 30-odd vessels at the moment around the globe. And the future is, because we gained experience from energy storage systems and hybrid propulsion system, we are writing prescriptive rules now, as we speak now, and an additional class notation for hybrid systems. So why we need to use this current method, because we don't have the prescriptive rule, is because the hybrid systems or battery energy storage systems are considered as an unconventional systems. The reason being, as per the class rules and SOLAS, the generators are considered to be the main source of power. Battery is considered to be an emergency source of power. What we are using as an emergency source of power for the main propulsions. So that's why we need to use this unconventional design risk assessment methods. The diagrams at the bottom is the risk assessment. How do we follow the risk assessment to ensure the systems are safe? After doing the scoping study, and then we look at the risk associated with the systems, what can go wrong, and if something goes wrong, and how do we mitigate that scenario. And once we done the risk assessment at stage 2, we move to stage 3, and where we implement those risk assessments. And at stage 4, we look at the operational aspect, the risk associated with the operational aspects. Stage 1, 2, 3 is about design aspect. Stage 4 is about the operational aspect. And the flow diagram on the right-hand side bottom is about how do we do a risk assessment for a battery installation systems. So a few of the reference cases, I would like to bring out few cases where an existing ship is converted into a hybrid system, as well as a new build vessel how we install hybrid systems. This was a Scandline vessel operating between Denmark and Germany. The owner's requirement was to comply with the ECA, 1st January 2015. They looked at these 4 options: run the vessel on MGO or LNG, or install scrubber, and or batteries with the hybrid propulsion system. They've installed batteries, and say 2.6 megawatt hour battery with a hybrid propulsion system. That was the route they have taken. What they have done is that there were 5 generators on board that vessel. They replaced one of the generators with a battery power pack. So as a result, they have removed this generator, and which is, in fact, by removing generator and installing that battery system, they also saved substantial weight on board the ship. This project has got an IMO Energy Efficiency Award as well in 2014. This was Europe the first tug which is converted into hybrid. A company called Cortec, they named this as an EcoTug in 2014. So they have installed battery on board in addition to the conventional propulsion systems. So at a low speed, the tug can operate, in fact, on 100% on batteries. So as a result, there is 50% less in emissions and noiseless operations. And the learning from this for the conversion, and Cortec has ordered 2 more vessels, RT Evolution and Emotions. So these are vessels designed by Robert Allen and built by Diamond Shipyard, where they got a lithium-ion battery of 117 kilowatt-hour installed, along with the conventional engines. And this is a reference case for a ferry. It's a new-built ferry operated by Caledonia in Scotland. The company has got a target of cutting down the emission by 2020 by 5 to 10%. They looked at 3 different options: diesel, mechanical, and diesel electric and hybrid, and finally they have gone for a hybrid systems. And talking about the tug, and for example, less than 5% of, on the diagram, it's on the left top side, less than 5% of the time the tug operating on 100% propulsions. So say around 40% of the time the tug operates only 25% of its power. 1 minute, sir. Yeah. So that low operations, the low power operations are basically on a standby mode or an idle mode or a towing mode or a harbor mode. So we don't need, the tug actually doesn't use its installed power all the times. So hybrid propulsion could be, the battery operation could be an ideal scenario. But if we have issues, because as per LR current bollard pull test procedure written in 1992, that's for the conventional engines, where we estimate the maximum bollard pull, steady bollard pull, effective bollard pull. But on a hybrid system, the power from conventional engine and battery system could be more than the conventional engine. So we may have to consider a scenario where we look at evaluate the bollard pull on a diesel only mode or a hybrid as well as a hybrid mode. Concluding, the hybrid and integrated power management system, though it introduces additional risk because there are no prescriptive rules at the moment, we consider this technology is quite matured because we have been able to class 30-odd vessels and they are still in operations without any issues, in spite of those battery issues, hazard issues what we have highlighted. And most of these vessels with certain operating profiles like tugs, OSVs, and passenger ferries and yachts are suitable for this type of propulsion systems. And we actually take care of the risk associated with the systems, identify all the hazards, and we are also working with battery or energy storage system manufacturers as the chemistry evolves. We also look at the hazards identified with the systems, both internal and external. So based on experience what we gain with the hybrid systems, we are writing at the moment the rules and regulations for hybrid propulsion system, which is going to be a prescriptive rule. We are working with academia, the flag states, and equipment manufacturers on this. There is an issue with the hybrid propulsion system. How do we do the bollard pull estimation and certifications? Our new hybrid propulsion system rules are going to address all these issues which are currently not covered. For example, DC network architecture, and as well as the new energy storage devices like fuel cells, supercapacitors, batteries. Thank you very much.